So this one we're saying a student is performing an experiment in which protons with a horizontal speed of 10 to the 6th meters per second enters a region with a uniform magnetic field of magnitude 10 to the negative second teslas as shown above. The student observes the deflection of the proton by the magnetic field and in analyzing the data ignores the effects of gravity on the protons. Does the student need to revise the analysis? Why or why not? So number one, what we want to do is let's kind of look at the magnitudes of everything. So like how much is the magnetic force, how much is the gravitational force, and we're pretty good at that. We can definitely do that. So let's do a quick little bit of math to figure out the magnitude of the magnetic force. So we know our equation for magnetic force is QV times B for a particle, and it's a little bit tricky because again, we may not off the top of our head know the value of the proton, the charge of the proton. So we're gonna have to look at our good old equation sheet. So it doesn't tell us the magnitude of a proton, but the charge of a proton is equal to the charge of an electron. So we know that the charge of a proton is 1.60 times 10 to the negative 19th coulombs. So let's plug that into our equation for Q. The charge of our proton is 1.6 times 10 to the negative 19th coulombs. The velocity that it's shot with is 10 to the 6th meters per second. And the magnetic field is 10 to the negative second. All right, so then when we plug that all in, we get a magnetic force of, let's see, I already did it, 1.6 times 10 to the negative 15th newtons. All right, so this is our magnetic force. Seems pretty small, but let's check the gravitational force because who knows? So we know gravitational force is mass times g. Again, we may not know the mass of a proton right off the top of our head. That's where our equation sheet comes in. So the mass of a proton is 1.67 times 10 to the negative 27th kilograms, which is pretty dang small. So let's plug that in. 1.67 times 10 to the negative 27th times 9.8. So we get a gravitational force of 1.63 times 10 to the negative 26 newtons. So right away we see that this is so much smaller than our magnetic force, which lets us know we can probably discount this. One other thing that we want to look at, actually let's look at our answer choices. So we say, hey, we can probably discount it. Reflecting the effects of gravity will introduce large errors. Probably not, that doesn't make any sense. Well, we see that it won't be large errors actually because it's such a small number. Just because all forces must always be included. Yeah, not necessarily. If it's so small, we can treat it as 0. No, because the magnetic force and the gravitational force on the protons are both directed downwards. So we didn't check the direction. Let's go back and do that really quick. So we know the gravitational force acts downwards because that's the way that it points towards the Earth. We do our right-hand rule. We say, hey, this is the direction of our index finger. So V, the magnetic field is out of the page. So that means that B, no, does it say QV? Oh yeah, just kidding. And then your thumb points down. I know how a hand works. Sorry. Yep, then your thumb points down. So they are pointing in the same direction. So we know that, but whatever. That's not really a reason to discount them. This is really a reason to discount it. The fact that it is so much smaller than the magnetic force. So we say, hey, this is so much smaller. It's almost 0 comparatively. So let's discount it. All right, that one's a little tricky, but yeah.